Okay, good morning, everyone. So for this second week, I'm gonna discuss. We will discuss about sorry, data exploration and preprocessing. So I think if you remember last week, I mentioned several times about how important data preprocessing is, because if the data is not good enough to be processed by any data mining algorithms, the result will not be good also. Yeah, the result will, maybe for example, the result is not valid, or the accuracy will be very low. So data exploration and preprocessing, these are two steps that we will be discussed today. Yeah, because these two steps usually we even sometimes we spend more time in these two steps. Okay, first is exploring the data. Okay, basically, the data exploration, maybe some of us already know about data exploration when we study about in statistics. Yes, so data exploration is basically, this is the preliminary exploration of the data. Okay, with data exploration, it can help us to guess or to analyze which algorithm or which tools suitable for this data. Because maybe you can imagine, if we are a doctor and the data is the patient, it means that every patient that come to doctor, it is customized, right? Because everyone have their own problems. So this is also happen with the data. So every data has its own problem. So it is very needs to understand the data, and before we decide, oh, this data need this kind of preprocessing techniques. Yeah. Okay, so first, why we need data exploration? Because it can help us to select which is the right or which is the suitable preprocessing techniques for this data. Okay, um, in some of the process of this data exploration, it will need a human's decision, because this one, people can recognize patterns not captured by data analysis tools. So in our data exploration, we need human decision, because our brain is we can capture some pattern from the data which cannot be captured by data analysis tools, cannot be captured by computers. Or maybe computer can capture that, but it needs like more complex process. Yeah, so it's sometimes most of the time it will need a human decision about this step. Okay. Okay, so data exploration data analysis, basically it will be focused on visualization, data visualization. Okay, and from data visualization, we can, for example, we can, oh, the data have some outlier, for example. Yeah, or the data have, for example, if we talk about clustering, then, oh, this data is quite difficult to cluster. Yeah, or if we talk about time series data, from the data visualization we can understand, wah, this data, the pattern is very complex, for example, too many noises. Yeah, so this is what we get from data visualization. So data visualization is one of very important step in data mining. Okay. Okay, so this is our discussion for exploration data analysis. First, that summary for statistic, and then visualization. For summary statistic, this is a basic statistic. I think I can review fast this part. So in a summary statistic, at least we can understand, or we can capture information about data location and spread of the data. Yeah, so if we talk about, oh, we are going to analyze data about our students, about the grade of the students. Then before we talk about the data, because before we analyze the data, at least we know what is the condition of our students. For example, the range of the grade of our student, maybe for a final exam, for example. Oh, our student is quite smart, so the value, also the score for final exam, it is around 80, 70, 80. Yeah, so at least in that case we have information, because the score can be from 0 to 100. Right? But from this statistic summary we can get more detailed information. For example, from location we can get information, the data between 0 and 100, or maybe around this area. And then the spread, or the how big is the range of the data. Okay, so to get that information, usually for the data, at least we can analyze from the frequency, mode, and percentiles. Okay, then for the measure of location, that the one that I mentioned, if this is from 0 to 100, location means that between 0 to 100, in which area our data. For example, our student is smart, so the score is around 70, 80, so maybe this area. Okay, and to get this information, we can use like median, mean from the data. Yeah, median or mean. So median and mean is they are two measurements that can give us information about where is our data located. Yeah, so where is our data located? Okay, and then for the measurement for the spread, it means that, for example, the one is 0 to 100. From the mean, we get the mean is here, maybe 75. Okay, but we don't know this 75 is the mean or location. Okay, but how far our data, the spread of our data. So the spreadness of the data, we can get that information from range and variance value. Yeah, so the range may be from 860 to 100, for example. Yeah, so this is the range of our data. It means that in range 0 to 100, our data they are within 60 to 100. Yes, so from this information we can get better information about the data. Instead of we think that the student's score is between 0 and 100, we can get closer information is 60 to 100. Okay, yeah. So this statistic analyze descriptive using this basic statistic summary. I think this is the one that we used to have this knowledge about this, right? So I can skip this part. Okay, now about data visualization. Okay, so the main objective to data visualization is we will arrange our data into a more, clear picture, because basically our human brain, we are easier to capture some pattern from the data if the data has been represented in some visualization. Now, so instead of see from, for example, like this wording or numbers, we are more easier. It is very easier for us to understand the pattern if we visualize the data. Okay. For example, this one is what we call this data. They show the sea surface temperature, for example. Yeah, the of course the real data. Maybe we can imagine that the real data is, this is the coordinate x and y. Latitude and longitude. This one. and then this is the temperature, number, so many numbers. Okay, for us, it's very difficult to capture the pattern or get information if the data is presented in numbers like this, right? But once we visualize into one picture, for example, like this picture, we can easily get information from this picture. For example, the sea surface temperature for some area like this, maybe in this area, it's very cold. But in some area, for example, like this, the red one, the sea surface temperature is higher than the one in the below. Maybe this is near the polar. Yeah. Yeah. Okay. See, so this one help us to get information easier, very fast, even faster than if we apply some data as some algorithm, some here or computation using computers to get information from this graph. Yeah, because our brain is easier to understand the picture. Okay, this one. Data representation. Representation is the mapping of information into visual format. Okay, yeah, so this is the formal definition about data representation. Okay, the data objects, their attributes and relationship among the data objects can be translated into graphical elements. For example, we can use points, lines, shapes, and color. This picture before, it used color to represent it, the data. Okay. Okay. Besides the data visualization using the picture, for example, like in the first picture, we also can arrange the data to make it more easier for the visualization. It's more easier to get the pattern. For example, the left one, this is the data. Let's say this is the correlation, for example, correlation between this is for x, for example, this is y. 0 means there is no correlation. 1 means that there is correlation between the element x and y. For example, 1 1, so this is no correlation. 1 and 2, they have correlation because it is 1. Okay, so from this data, if we see the left table, for us maybe it is so let's say it's very messy, so we cannot get the pattern. But here, if we rearrange our data, for example, in the right side and the left side, these are the same data actually, but with different arrangement, we can easily get the pattern. For example, we can see, from this data we see that 4, 2, 6, 8 have correlation with 613. Okay, but for 5, 3, 9, 1, 7, it has correlation with 2, 5, 4. Okay, from this. Yeah, so maybe sometimes we need to rearrange our data format to make it easier to get the pattern. Okay. Okay, maybe later I will talk about this. Okay, visualization techniques. Basic one, for example, we can use histogram. Of course, that histogram is a table like this, for example. I think we already saw this histogram in many times, right? This is the histogram. So I think for this visualization, I will introduce you for one data set that this data set is very well known. This is the iris flower dataset. So I will use this dataset to introduce you some data visualization. Yeah, how to implement the data visualization into data. I use one dataset which is very well known. This is the iris dataset. So this one, this dataset, we can get this data from this link. This one is the UCI repository. It is one repository that publish so many dataset. So I think I can show you the link first. Oops. Mm. Yes. Why I can open with. Okay, this one. This is the UCI repository. Okay, this is the these are some data set that we can use because because this website give us so many data set. So maybe for your research you also can apply your algorithm into this data. Usually when we use this data set, for example, if we want to validate our algorithm, yeah, so we can use this data set. Or for practicing, yeah, we can also use this data set. This one is the iris dataset, the first dataset, because very famous. Yeah. Again, this website already give the information about this dataset. Okay. So what is iris dataset? Iris dataset basically, this dataset consists of 3 types of flowers: Sontosa, Virginica, and versicolor. Okay, and the dataset, these 3, they call it, this is the class of dataset. So this is supervised dataset. Okay, iris is supervised because it has classes. Okay, and beside class they have 4 attributes, which are sepal width, sepal length, petal width, and petal length. So the data, there are 4 attributes: the sepal width, sepal length, petal width, and petal length. And of course they also have class. Yeah, so they in total they have 5 attributes. Okay, 5 attributes. One is the class. This, for example, the picture of the data, the picture of the flower. Okay, they try to differentiate the 3 different types of flower based on the size of petal and sepal. Okay, so the data, basically the data have 4 attributes. Okay, so it is for the data more than 2-dimensional data. Usually it's more challenging to do the visualization, because if the data is only 2 dimension, then it's easier, we can just use X and Y. Yeah, but if data have more than 2 dimension, then we should do something, yeah, for this data set if we want to visualize the data. Okay, for example, this is the histogram. We can use the histogram, but we know histogram is only for one attribute. For example, like this. This is the first attribute, for example, petal width. Okay, I think this is, I get wrong. I think this is different attribute. I forget, sorry. So we have 4 attributes, 1, 2, 3, 4. But histogram, for example, like this, histogram only can show us for each, this is the simple histogram, I mean, for each attribute. So maybe if we have 4 attributes, we can give like 4 histogram, I mean, for each attribute. But we also can combine 2 attributes. For example, we combine petal width and petal length. Okay, so here we can see that from this data, for example, or if the peta width is from 0 to 1, for example, and the peta length is from 0 to 3, they're around maybe 30 data here. They are in the data set, they are around 30 instance which has peta width size and peta length size between 0 to 1 or 0 to 3. Okay, so we also can combine two attributes. Okay, box plot, we can use box plot to identify outlier. Actually, sometimes by our eyes, we can get information. For example, this is our data scatter plot, for example, and this is one data very far away from other data. We can see that, oh, okay, this is outlier. But be careful, because sometimes, for example, like here, is it outlier or not? Okay, maybe okay, so human can get information from data visualization easier, but sometimes human also can get different decision, because we like subjective. Okay, so for example, for outlier, we can utilize box plot to identify which one is the outlier. Okay, this is, for example, this is the box plot. Yeah, box plot will give us information. For example, this is the data, the most of the data. This is the 50 percentile of the data. This is the 70 and 25 percentile. And we have this one and this one. Let's say this is the upper bound and lower bound, which are the 10 percentile of the data. And if the data is out of this range, then we can identify that as outlier, for example. Okay, but if we have 4 or more than one attributes, then for each attribute we can apply box plot for each of them. Yeah, this is an example of box plot if we have more than one attribute. Okay, and we also have scatter plot. Yeah, scatter plot, it's most commonly scatter plot in 2 dimension, but sometimes it also have 3 dimension. But if we have more than 3 dimension, then we have to do something with the data. Okay, maybe we can apply that dimensionality reduction. Later I will discuss about dimensionality reduction. Okay, yeah, this example of the scatter plot for iris dataset. Okay, because we know for example, the scatter plot, it only can give us a picture for 2 dimension or 3 dimension. But iris have 4 attributes. So what we can do is we can do like this. These are all combination of 2 attributes from iris. For example, the first box in the lower left here, it gives us scatter plot between sepal length and petal width. Yeah, and in the next picture here, it combines sepal width and petal width. And the next one, petal length and petal width. Yeah. Okay, so this one example. If we want to visualize the data using a scatter plot, but the data in our hand is more than 3-dimensional data. Yeah, so we can combine like this. Okay, and this data also utilize color to represent the class of the data. Yeah, so we can combine line, shape, what else? Line, shape, like this, point, and also color to represent our data. In this picture, class represented by color. So different color, different class. Okay. So for example, what kind of information we can get from this data? Okay, let's see. Maybe the first thing you can see here, we can see here like in most of the picture, the blue one, the class blue, relatively well separated than other color, right? From here, here, and here. This one also, this one also. Yeah. The blue one belongs to Sentosa class. So from this data, at first maybe one information we can get is for Sentosa, the flower Sentosa, this type of flower is very different than versicolor or virginica. That's why in the picture it is well separated than other two classes. Yeah, we can see this. But for the two class or the two types of color, the two types of flower, versicolor and virginica, for example, in most of the picture they are mixed. For example, like this. Here, which one? This one will be a little bit. Oh, okay. So for this picture, in terms of sepal length and sepal width, for example, versicolor and virginica, maybe they're not very different to each other for these two classes. That's why here the class is relatively mixed. Yeah, so maybe for versicolor and virginica, sepal length and sepal width that not really different. That's why they point like mix. Okay, but if we compare in terms of, let's see which one is well separated. Maybe this part, this picture, I think. Yeah, or this maybe, or this. Yeah. In terms of petal width and petal length, versicolor and virginica, they can be different. Yeah, compare with sepal length and sepal width. So the sepal of virginica and versicolor, they are quite similar. But for the petal size, petal width and petal length, virginica and versicolor quite different. From this picture, we can get that information. Okay, so maybe we can say that, maybe to differentiate between versicolor and virginica, we better to see the petal size instead of sepal size, because from these two picture 1 and picture 2, petal size can differentiate between versicolor and virginica better than using sepal. Okay. Yeah. So this kind of information we can explore from the data visualization. So this one, what we get, we can only use our eyes to get this information. Of course, our eyes and our brain to get that information. But maybe if we use computer, we ask computer to get this information, it will need more complex calculation, right? Okay, so only from data visualization itself, we can get more information. Yeah. So, okay, data visualization. Okay. Another techniques to visualize the data. Also, we can use contour plots. So contour plots. This one, for example, this is the contour plots. One example of contour plot. Yeah. The contour plots is useful when a continuous attribute is measured on spatial grid. Spatial grid means like this, for example, a different on each location. So we talk about different location. Yeah. So if, for example, we want to we have the data about population size from all country. Yeah. So that one, we talk about different country, then we talk about different location. So we can use contour plots, for example. Okay, and then The most common example of contour plot is contour maps. Yeah, for example, like that, contour maps. But it also can display, for example, temperature, rainfall, air pressure, because, for example, temperature in different area, they're different. Rainfall rate for different area, of course, they have difference. Yeah, so the key point here is this one. We can use contour plot if the data we have from, for example, different location. Okay. What else? We can have matrix plot. This one. This one is the example of matrix plot. Yeah. So this is the iris dataset, and these are these attributes for each. For each attributes, and then. This is the class. So for class Virginica, for example, the SEPA length, this is from the data, for example, that we can get from here. This one also the visualization matrix, but this one between two classes. We combine between two classes. Okay. We also use, for example, parallel coordinates, to get the data. And this is the parallel coordinates. Okay, so this show us each attribute. Okay, this is the value of each attribute with different color, different class. Okay. Okay, so if we use Python, so in this class, actually you can use any kind of tools to visualize the data. I just show you one example. If we use Python, so in Python they already they provide us with this one, very comprehensive library for data visualization. So if we go to this website, okay, Matplotlib is one library for Python, package for Python to visualize the data. And here we can see, for example, this one. They show the all gallery example of the data visualization using Python. For example, this is the stack bar chart and horizontal bar chart. This one, the example of the data scatter plot, and this one, image contour and fields picture, data visualization. Okay, this one, for example, matrix data, matrix color. So actually this one using this one, if we want to combine subplots, so we have more than one plot in one picture, for example, like this. They also give us how to write the program. We can just use their package. This one is statistics, basic statistic for data exploration. What else? Pie and polar chart, even text. They can show us, and many more. Yeah, this one using shape. Yeah, so many. There are so many examples. You can explore this, and to use this, it's pretty easy actually. We can back here, for example. Let's start for example, this is a simple plot. Yeah, so we only use for this one. This is very few comment if we want to use the plot. Of course, this is the simple plot. Okay. This first we have to import the library matplotlib, this one, and then we can call all this one, This is the basic function, for example, for the plot. Okay, for example, if we want to, I have this data, using this command, I can get this simple plot. Okay, and what else? This is for scatter plot. Scatter plot, basically we can just write PLT. PLT refers to matplotlib, this one, and scatter x, comma, y. Okay, and then we can get this result. Yeah, this one for bar plot. Yeah, here bar, only this line 18 can use bar. This one, if we want to combine scatter plot with different color, represent different class, for example, so we can combine. Okay, so this how to, I also learn by myself about this because it's not really complex. So what I did before, for example, I choose which one of data visualization I want to follow. For example, I use, let's start from the easy one. Which one is the basic one? I use the easy first for example. Oh, this is already animation. Yeah, they also, you can also use this too for animation. So I think the easy one should be okay. This one is scatter plot for the MATLAB. Sorry, using the Python. Okay. So here, why they don't give us the picture? Sorry, wait. Oops. So does anyone familiar already with the Python? So it's easy, for example, like this. So if this we are new in using here, we can choose the picture, okay? And the first step, usually at the very beginning I learned about this, I just copy all of this. This is the example, okay? Then in our example, they will give us the example of the data set. For example, this is the data. Okay, so later we can use this code, but we change into our data. Yeah, so it's easier for us to use. Then we can get this, for example. Okay, any question before I continue to data processing?
So far, so good for me.
Okay, so you can check to this if you want to use different visualization. You can go to this example. Okay, I mean go to this website. Okay, we continue to data preprocessing. Okay, we use data preprocessing because the real data is dirty, means that it is incomplete. We can get incomplete data, some noise, of course, and sometimes it is not consistent. Okay, so we have to preprocess the data. Okay, some example, some reason why the data can be incomplete. For example, the attribute of interest are not available. For example, customer information for sales transaction data maybe is not available, or maybe our data collector cannot give for example, they don't, or the respondent, they are not willing to give all information about themselves, for example. Okay, or the data maybe they are not recorded because of something, and many other reasons. So the data is incomplete. Data also can be noise. Okay, I have the noise and inconsistent because, for example, some error with the instrument during the data collection, for example, and many other reasons. Okay, so in data preprocessing, this 1, 2, 3, 4, 5, 6, 7, 8. There, for example, there are 8 major tasks in data preprocessing, but actually we can do more. Yeah, this is just some basic data preprocessing techniques. For example, the first one is data cleaning. Okay, in data cleaning, at least we have to make sure no missing value. Okay, no missing value because of course missing value can give us a problem. Okay, and we also can do outlier identification, or we can delete the noise of the data. And of course, we also have to correct the inconsistent data. Yeah. Uh, this one, how to handle missing data. I think we can use, for example, we can ignore the tuple, like last week we discussed. Okay, we also can fill the missing value. Okay, and missing value, for example, no, I don't give example. Sometimes missing value, for example, we have 3 attributes. For example, maybe this is the age, and then this is the education, and then this one the salary, for example. Okay, we have data, but maybe one of this is missing value here. The easiest one we can get, because salary is continuous, the data is continuous, so we can feel like we have the average, and then we fill this value. This is the easiest one. But sometimes we also can, instead of using the average of all instance, here we can only use average or mean only for all samples belongs to the same class. For example, we know, for example, education, in our hypothesis, education will influence the salary, for example. So instead of average all of this value, we see first this missing value, what is the education. For example, this is the PhD. Okay, so here we will find other instances which the education is also PhD, the same one. So for example, instance number 1 and number 4, they're also PhD. Okay, so here instead of using all data 1, 2, 3, 4, we only take the average of the salary from data 1 and data 4. Why? Because data 1 and data 4, they have the same education class with data 2, which is the missing here. Yeah, so we can also do this to get more accurate prediction for the missing value. Okay, noise data, this one, if we have the data, some noise in data, for example, because of the instrument, we have some problem with the data collection and technology limitation and data transmission or other things. Okay. We also have to be careful with duplicate records, incomplete data. Yeah, because maybe it is data cleaning for duplicate records. Be careful. Okay, how to handle noise data? To handle the noise in the data, sometimes we can use smoothing techniques. Okay, for example, this we have binding methods. So the first binding methods is to make the we can sort the data, divide it into several bins, and then we can smooth by bins means, median, or boundary. Okay, and then we also can remove the outliers to make the data more smooth. Because for example, if we have time series data, then we have outlier like this, maybe we can delete this so the data becomes more smooth, for example. Okay. In smoothing data to delete to handle the noise data, we also can combine computer and human inspection. Yeah, so like we visualize the data. For example, we visualize the data and using human decision to see, oh, okay, we can delete this, for example. We also can do regression. Yeah. So in data regression, we use, for example, we use regression model to get a smoother data. Okay. Then we have data aggregation. Data aggregation means that this one. The data aggregation is the process of gathering the data and present it in a summarized format. For example, we can combine two or more objects into a single attributes. Sorry, more attributes into single attributes, or we can combine some objects into one object. For example, why we use data aggregation, because if we reduce the number of attributes, for example, we can get the data size become smaller, so the memory needed to process the data uh, smaller also. Right? So if the memory is or the data size is not big enough, we can use more complex algorithm because it's faster. Okay. And then we can change the change of the scale. For example, we aggregate the cities into some region. Okay, maybe for this one, let me give example. Yeah, this one, reduce number of attribute. For example, we have sales. We have the data. This is the price of the product, and then this is the text. The text we know, for example, text is 10% from the price. Okay, so basically these two data, they are related to each other. Yeah, for example, if the price of if the product is 1,000, then the text is no 1. Yeah, sorry, 100. Make it easy. Okay, so if the price of the product is 100, then the text is 10. If the product is 500, then the text is 50. Yeah, so these two attributes, they are basically related to each other. So instead of using both of them, we can just use we can just use price only. Yeah, so the number of attributes become smaller. Okay. The second one, if we use aggregation to change the scale of the data. For example, we have that in our data we have what country? No, not country. Maybe the city. Where are you? Where is your location? For example, then if we record in city, for example, maybe one instance in city 1, another instance in city 2, because city is there are so many cities, so maybe the variation of in one attribute itself, city, maybe we can be 100 cities, 100 different city, for example. But if we change this data, the city into the country, if we change city into the country, maybe the variation only, let's say, only 1 to 10 country. So it's easier to analyze. Yeah, we can aggregate like this. By aggregation, it also provides us high-level view. And of course, it will give us more stable data because aggregation data tend to have less variability. This is for example. So this is the standard deviation for monthly and compare with yearly perception in Australia. This is the standard deviation. Yeah. So if in monthly data, the standard deviation is bigger if we compare with the yearly data. Okay. Maybe the real data is like this. If it's monthly data, maybe like this. But for yearly data, maybe more smooth, or even maybe like this. Yeah. So it's easier for us to understand. And if we have yearly then instead of monthly, maybe we also can have high level view because yearly then we have many years. Okay. Okay, any questions?
Clear for me. Yeah.
Clear? Okay. Wait, yeah. If you have any question, please. Just want to make sure that do you see my slide
Yes.
in
Yes.
slideshow?
Yes. Some do.
Okay. Okay. Any question? No? Okay, we can continue to sampling. Okay, sampling. Yeah, sampling is the main techniques employed for data selection. Okay, so sampling focus on data selection. Yeah. Remember we have feature selection later, but sampling is data selection. So we choose the instance, not the feature or not the attribute. Okay. This is of data sampling often used for both preliminary investigation of the data and final data analysis. Okay, this is we can apply statistics sampling techniques. Yeah, because maybe if we use the entire set of the data, maybe it's too expensive or too time consuming. So in maybe we know if we apply statistic methods, for example, for statistic we have population, and then because we cannot get all data for the population, then we use sample. Okay, this is in statistic. In data analytic, let's say we have 10,000 data sets in 10,000 instance in our data, for example. Okay, but maybe we have limited computations capacity, for example, or we want to apply a very complex algorithm, for example. But if we very complex algorithms, processing 10,000 data instance, maybe it will take very long time. The time computational will be very, very long. So instead of using all of this data, 10,000 instance, we only use the sample of the data. Maybe we only use, for example, 1,000. This is the sample. Okay. So in our case, in data analytic, we do have 10,000 data, but we only process the sample 1,000. Yeah. Okay. In sampling, okay, we have to make sure that even though we use a smaller data set, but this smaller data set, the sample, it represents the entire data. Yeah, we have to make sure that. So this one, a sample is representative if it has approximately the same property of the original data set. Okay, so even though we use smaller one, but the property, the pattern is the same. Okay. We can apply similar sampling techniques in statistic. For example, we use simple random sampling, and then we also can use sampling without replacement or with replacement. We also can use that, or we can use stratified sampling. So we divided the data into several partitions first, and then for each partition, for each part, we can use random. We can use random sampling for each part. Yeah. For sample size, now how big is the sample size we can use? We can apply, for example, progressive or adaptive sampling. So we start with the small number of the sample, and then if we think that the accuracy is not good enough, for example, we from 10,000 we use not 1,000, maybe we use 500 first. But then after we process the data, the accuracy is not good. So we increase the number of the instance in our sample. Yeah, so we can apply these techniques. Okay. We have to make sure that we will not lose structure of the data if we sample the data. For example, like this. This is the original data with 8,000 points. Okay, so if we only use 500 points, for example, then you can see that, oh, the pattern is not clear. Okay, so in our algorithm, maybe we increase number of points in the sample. Yeah, so maybe with 2,000 points or the patterns, we can see a little bit about the patterns. Then it's depend on us if we whether we want to increase the sample size or not. Okay. We also can use alternative approach here. First, we take a small sample of the data point. Okay, and then we compute the similarity of the data points. Then we can form groups of points that are highly similar. For example, like this. Let's say this is our data. Yeah. Imagine this is, for example, too many data. And instead of using all of the data, we are going to sampling the data. So here we choose a small sample of the data point. For example, we only choose this one, this one, this one, this one. Okay, the green one for the sample. Okay, then we calculate similarity. The point here is if the data is quite similar, it means that the data is very close to each other. Let's say, for example, this one and this one. These two data very close to each other. I'll make it bigger. Let me write the bigger. For example, this data, they are very close to each other. This one, very close. Okay. These three is very close, very close. Okay. So here, instead of using 1 and 2, we just choose between these two data which one we are going to use. Okay, so for example, this is group 1, group 2, group 3, group 4. Here, from each group, we use only one data point as the representation. Okay, so if the data is very close to each other or very similar, we don't use both of them. We just use one of them to represent their groups. Yeah, we can also use this. Okay. Any question?
No.
No? Okay. Dimensionality reduction. Okay. This one. Most of the time we work with the data which has so many dimensions, especially now, because now it's very easy. Sometimes it's very easy to get the data. So maybe when at the step of the data collection, we think that okay, we just collect as many as possible the attributes of the data. But then processing the big data, it's more difficult, of course, than the small data. Okay, and also, for example, some data mining algorithms, it works better if the dimensionality is low. Dimension here refers to the number of attribute, not number of the data. Okay, dimension is the number of attribute. Yeah. Okay. So here we are thinking how to reduce the dimensionality of the data. Okay. This is the benefits of dimension reduction. Again, some data algorithm maybe work better, and we can also reduce. It is more understandable, yeah, because I have lower attributes, and the data, of course, it is easier to visualize. Okay, and of course, the time and memory to process this data will be smaller. Okay, here, okay, some methods. There are many methods to reduce the dimension. Okay, the purpose is to avoid curse of dimensionality. This is the purpose of dimensionality reduction. What is the curse of dimensionality? Okay, so when the dimension is increased, the data becomes increasingly sparse in the space that it occupies. Yeah, so be careful with this. Why this increasingly sparse in the space will give us more difficulties? Because again, the pattern will be more complex, so it's more difficult for us to capture the pattern. Okay, the same happen with the if we are going to use clustering, for example, or outlier detection. Yeah, because the attributes is so many, so maybe because it will makes the density of the data or the distance between data points become more vague. Yeah, so we cannot get the patterns. Okay, so here the purpose of dimensionality reduction, basically the main part of the purpose of dimensionality reduction is easy to process because it requires lower time and memory. Okay. Methods for dimensional reduction. First, we can creating new features that can represent all features. Of course, the set of all new features is less than the set number of old features. Yeah, so here the keyword is creating or selecting. Okay, so these two are the main methods for dimensional reduction. We can totally create new features, or we can just select some attributes. Creating means that if we have 1, 2, 3, 4 attributes, creating new means that we will have, for example, the new one, or let's say A and B. Yeah, of course, this A and B represent all feature 1, 2, 3, 4. Yeah, so 1, 2, 3, 4 is the combination mix. So these are mix. and then create new. Okay, so we cannot we don't know whether A is only belongs to 1 and 2, B is belong to 3 and 4. No, this is not the mechanism. Creating means that we combine, mix all of these all features, and then create the new one. Okay, creating, for example, we can use principal component analysis, singular value decomposition, for example. Yeah, basically these three algorithms they develop based on linear algebra techniques. Okay, yeah, these are creating new features. How is selecting? In selecting, we simply select between all features. For example, we have 1, 2, 3, 4 attributes or features. We select, for example, only select 2 and 3. We don't use 1 and 4. Yeah. So select means that we only choose part of them, only use some of them, and totally ignore others attributes. Okay. But creating, we will not ignore any features. We will mix them into the new features. Okay. This one is principal component analysis. So here, basically PCA, I call it PCA, it represents the data into a lower dimension of the data. For example, this is the left picture. The data, it has two dimension, X and Y here, or the this one. We have the direction U and V. We see that in terms of U, for example, the range of the data from here into here. Let's say this is V1, V2. Okay, so this data in PCA basically they will choose principal components. Let's say here the principal component is U and V, represent the direction of the data, U and V. Of course, U and V, they are U vector is oops, what happened this? U and V, they are orthogonal to each other, U and V. Like this, U and V is orthogonal. And then the data, we represent into, for example, I make it like this. This is U, this is V, for example. We have this data. So this data, for example, if we plot represent into the vector U, it means that the location is here. This is the data. This is the data in vector U. And this is the data in vector V. Yeah, the X in vector V. So we represent here. And this one, the principal components means that all the data will be make it the simple. I try to discuss in the simple way. So all the data will be represented in all principal component. For example, this picture, all the data we will calculate in vector V, for example. So this is here, this data here, and all the data. So represent in vector V. Vector V. So the vector V, maybe the data is like this, very close to each other. Okay, and we also will represent into vector U. Okay, vector U, so the data is like this. This one is here, here. Okay, so it's like this. Okay, so at the end, we will have U and V as the principal components. We have two principal components. Okay, so in principal components, later after we represent the data into each principal component, we will choose which principal components will show the higher variety of the data. For example, this is the vector v and this is the vector u, v and u. Okay, the vector v variation is only, for example, like in this range, but vector u from here to here. Yeah, so maybe in this case we can see that vector u can give us information more about the variation of the data. Okay, so instead of using u and v, we can just use maybe only vector u. We can ignore vector v because the variation in vector v is less than vector u. Okay, yeah, this is a basic concept of PCA. In PCA, actually, if you ask me, okay, we have x and y, and then we convert into u and v, and between u and v, we only choose u, for example. So we change from two-dimensional data into one-dimensional data. And then if you ask me, okay, we choose u instead of v, or instead of u and v. But is this u represent x or represent y? The answer is u represent both x and y. Okay, so in our case, for example, we have the class of data. Let's say we have the age, we have the education, for example, and then we have the salary. Salary, let's say salary is the class, high or low, for example. Yeah. Then to predict salary, we can use X as age or Y as education. But here, for example, I want to eliminate one of, I want to reduce two dimension into one dimension. Then you ask me, okay, I use U, principal components. But then you ask me, also to predict the salary, which ones, age or education? I don't know. Yeah, because my principal component U, they already represent age and education. Okay, so here, because okay, this one, pro and cons of PCA. The advantage of PCA, it can deal with large data set. Okay, but then there are no special assumption on the data, and PCA can be applied on all data set. This is the pro of data of the PCA. But here, usually this is the most common problem find with PCA. The meaning of original variable may be difficult to access directly on latent variables. It means that in our case, we cannot know which one between age and education give more influence into the salary. Yeah, because you represent all of this. Okay, so because of this disadvantage of the PCA, usually PCA used for example, image processing. Okay, this is the image processing. For example, this is the real data, very clear, 0, 1, 2, 3, 4, 5 until 9. Okay, then we use PCA to reduce the dimension. Okay, this a little bit blur, but we still can see the pattern right here, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, why in image processing like this PCA is very common to use? Because dimension in the image is not really have the meaning, like in compare with, for example, this our data age and education. So in image processing, the first attribute doesn't really have any meaning. Second attribute and until all attributes. But in our data, for example, usually in our problem in industrial engineering, for example, attribute 1, age. Oh, age have a meaning. It's the age. Education have a meaning. Oh, it is the education. Like this. Okay. Okay. If you are going to apply PCA in Python, you can just use this. Already have the function, or again already have the package. This one, sklearn decomposition. And in this package, sklearn decomposition, it has a PCA. Okay, so the PCA here is pretty easy. Okay, only this 1, 2, 3. The 21 is only to I just want to print. Okay, so it's very easy. This one. Okay, very simple. We can use this package. So here I use PCA, for example, to represent, this is the iris dataset. Okay, so this is the dataset. We know that iris have 4 attributes actually, but I use the PCA to reduce the dimensionality from 4 to only 2 dimension. Okay, but here the x coordinates is the first principal component, and then the y is the second principal component. I cannot say this is the sepal length, for example. No, I cannot say this. This principal component 1 is already combination of 4 attributes. Second principal component is also the combination of all attributes. Yeah, so here you can see that although we reduce the dimension, we can still see the pattern of the data. Let's say, I hope you still remember, this is one class very separated from other 2 classes, and this is other classes. So maybe here divided like this. Yeah, so the variation of the data still can be captured. Okay, any question? Have you ever applied PCA before?
But Dr. Ferris, I mean, PCA in the SPSS is the same, right? I mean, the concept like this one.
Yeah, I think.
Yeah, I think more or less like by this is by Euclidean distance, right? So I think this is it. Or
I never use PCA using SPSS. But if the indeed SPSS say that it is principal component analysis, then of course it is the same thing.
yeah, same thing, right? So
Yeah, okay.
yeah, it should be the same thing, right? But
Should be the
anyway,
same.
how can we know if that one reduced into 1 or 2? I would say like dimensions. How can we
Okay.
know? Because if we see, I don't know, sister, I'm a SPSS person, so
Mm-hmm.
yeah, so I can see that one like you can be grouped into 1 or 2 or 3 by the Euclidean distance. And what about this
Yeah.
one? The judgment, yeah, for this one.
Okay. So if we back to this picture like this, we can write like this. If we have, for example, we have 4 dimension, okay, then we will have 4 principal component, PC, principal components, okay. So each principal component will have a score. It's, for example, PC1. What did I write? Wait. So each principal component has a value: principal component 1, principal component 2, principal 3, and principal component 4. So this one have value about how big is the variation of the data. Data variation represented by each principal. Okay, let's say for example, PC1 it has 0.5, PC2 has 0.3, 0.1, 0.1. For example, of course, in total they have one. This one I mean this is in the percentage. Okay, so principal component 1 can represent 50% of the variation of the data. Principal component 2 can represent 30% variation of the data. Principal component 3 can represent 10% variation of the data. Principal component 4 can represent 10% variation of the data. Okay, so if we do the accumulation, PC1, 0.5, PC1 plus principal component 2, 0.8, principal component 1, principal component 2, principal component 3, 0.9, 1, 2, 3, 4, okay, 100%. Of course, we use all of them. Okay, so here, if you ask me, so from 4 principal component, how many principal component we should use? Then it's depend on us how many percentage variation of data we are going to include in our next data processing. For example, maybe I just use 80% variation of the data. So it means that if we use 80% here, it means that we only use principal 1 and principal component 2. But if we think that no, 80% is still too low, I need to increase into 90%. So it means I have to use this one. 1, 2, 3. Okay.
Okay, yeah. It's
Yeah.
the same. Yeah, the same. Yeah, basically.
Mm-hmm. Okay. So that's why in this one I print explain variation ratio, because I want to know how big is the variation use. I mean, how big is the variation of the data left if I only use 2 principal component. Okay, other question? Can you give me 2 minutes? I want to take some drink.
Sure, no problem.
Okay, continue. Okay, then next part is feature subset selections. How we choose some features. Okay, so this one is different with PC feature, creating new feature. This one creating. The next part is if we select only some features. Okay, this is another way to reduce dimensionality of the data. We use only some features. Okay, we basically prefer these methods to reduce the dimensionality if we want that our subset of the features still have the meaning. Yeah, for example, to predict the salary, we still want to know between age and education which one is used to predict the salary. Yeah, we still want to know the original meaning of each attribute, so we prefer to use these feature selections. Okay, in feature selection, first that we can eliminate redundant features. Sometimes the feature have redundant information. Yeah, for example, the one that I give you example, the purchase price of the product and the sales tax and the tax. Yeah, these two, although these two have different uh, data. One is about the price, one is about the tax, but actually both of them give relatively the same information. So we can say that it is redundant information, redundant features. We can choose uh, one of them. Okay, and maybe some features also irrelevant. Yeah, for example, contain no information that is useful for data mining text at hand. For example, of course, if we want to predict the student's GPA, we don't need the student ID, for example. Or maybe of course ID is very obvious, right? But maybe, for example, in our data we have the address of the student. Okay, so should we also consider address to predict the student's GPA? Yeah, I don't think so. Okay, so we can choose, we can eliminate irrelevant features. Okay, these are some feature selections techniques. First is brute force approach. So here we are brute force. So we try all possible feature subsets. Yeah, for example, we have let's say we have 1, 2, 3, 4. So we make all combination of this subset 1 and 2, 1 and 3, 1 and 2 and 3, for example. And then see which one of these features will give us the best result. This is brute force. We also can use embedded approach. So some algorithms sometimes in data mining it's already embedded with feature selections. Okay, so the algorithm itself will decide which attribute will be used, yeah, or which one is to ignore. Okay, so already embed with the algorithm. Uh, they also filter approach. Okay, the feature are selected before data mining algorithm is run. Okay, so we choose first. For example, we can use pairwise correlations. So if 1 and 2 have very big correlation, then we just choose between 1 and 2 because already have the correlation is very big between 1 and 2. But 1 and 3 correlation is very low, so we can use both of them. Okay. Wrapper approach. So use the target data mining approach as a black box to find the best subset of the attribute. Sorry. Okay, so these are some approach we can use to do the feature selections. Okay, so for the feature selection, this is the main architecture. First, we evaluate the subset. And then we have the search strategy that controls the generation of the new subset of features. And we also have the stopping criteria when we have to stop find the new subset. And we also have validation procedure. Okay, for wrapper method, the subset evaluation, it uses the target data mining approach. But for the filter approach, the evaluation technique is different from the target data mining algorithm. Yeah, for example, classification. So for the classification, the target data mining approach is to reduce to increase the accuracy. Yeah, for example, classification. Classification, the target is a high accuracy, for example. Okay, so the subset evaluation, we will refer to the accuracy. Okay, but for the filter approach, we can use different measurement. For example, correlation, yeah, different than the targeted. Okay. Okay, this is the dimensional reduction. In overall, we can use feature selection, or the one before, we can use feature creation. Okay, select minimum set of features such that the probability distribution in different classes given the value for those features is as close as possible to the original distribution. Yeah, so this is quite similar with the sampling, but dimension reduction, we focus on the attribute. But we have to make sure with the smaller features, we can still have the original, the pattern of the data. Okay. We also can use like heuristic methods, stepwise back elimination. I think if you are familiar with the regression, it's this 1, 2, 3. Similar with the stepwise regression. If you have in regression, we can have like we have x1, x2, x3, x4. Okay, so instead of using all of these all these attributes to predict y, for example, in stepwise regression, they will try to add one by one or reduce one by one. Yeah, this is a similar, exactly the similar idea. Okay. We also can use decision tree induction, but maybe I will skip this for now because I haven't teach you about what is decision tree. Okay. Next, beside eliminate some features, we also can create new features. So why we need to create some new features? Okay, because maybe uh, our data on hand, they don't really, they miss some information. For example, I want to predict number of students come to the school, for example. Then uh, every day I have the data. We have, for example, this is the day and this is number of students. Yeah, we have day 1, 2, 3, 4, 5, or the dates maybe. Yeah, date. For example, this is the date. Okay, so instead of using only day 1, 2, 3, 4, 5, logically, in logical, we can get information usually during the holiday. Number of students is less than during the weekend. Number of students coming to school less than number of students coming to school during the weekday. So here, uh, I will try to add one more features. For example, holiday, weekend or weekday, weekend or no, or weekdays. Yeah. So here we add one more features. Why? Because only dates or only day, it doesn't give us information whether that days is have class or no, for example. Yeah, so we add more information, more features. Okay. Uh, Three general methodology for the feature creation. First is feature extraction. The one it will need domain specification, like this one, for example. How do I know that? Oh, I need to add one feature, whether it has class or no, or weekend or weekday, because uh, I work in school, so I know the behavior. I pretty know behavior of the students. Yeah, so I know, oh, with what kind of features should be added into the data, because in that case I am the domain specific or domain expert in this case. Yeah, so this way to create a feature, we will need a domain specific or domain expert to give information. Okay, or for example, I want to predict electricity generated by solar panel. In that case, for example, I just have like periods, day, and then the the power generation. If I want to add more feature, of course, I have to discuss with those expert in solar panel, for example. Yeah, so this one in this case need domain specific. Okay, we also can use this one. We can mapping the data into the new space. For example, we can apply Fourier transformation or wavelet transformation. With this transformation, we can get more features. Okay. Later I will discuss more detail about this. Or we also can do, basically we do the feature construction. So here, from the original features, then we construct new features. Okay, and of course the new features should be more useful than the original features. Okay, let's see for the mapping. This is the time series data, for example. The original one is the first line. Okay, so instead of using one attribute time, for example, this is the time, year, this one, I will decompose this data into, first I have seasonal components, break down into a seasonal component. I also have the trend, trend of this, trend is this, trend of the data, and I have irregular irregularity of the data. So the original one, I only have t, which is the time, and the data itself. For example, here after I decompose the time series data, I can have the t, of course, the time, and then I have the seasonal, then I have the trend, and I also have the irregular pattern of the data. So I have more features. So hopefully with these more features, I can get a better prediction. Okay. Special for time series decomposition, also have wave flat and Fourier transformation also have the function or package in the Python. In MATLAB also has. Okay. Time series decomposition. This is decomposition special for the time series because time series data usually have at least this component, seasonal, trend, and irregularity. In the Python, we can use this one. The package is this one, what is this? Stat models TSA, seasonal, and here we can call seasonal decompose. Yeah, so we can use this to like this. Yeah, this is the original data, but then I decompose into three of these. Again, to use this is also very easy because here, because in this link, it's already give us the example. So like this, very simple. Okay, any question? No
No,
questions?
no.
Okay. Okay. Next, we have discretization and binarization. Okay, discretization. When we use discretization and binarization, some algorithm works well or works more efficient if the data is in discrete format or binary format. Oh, this one already read. Okay, so for specific data algorithm, sometimes it is necessary to transform continuous into the discrete. For example, data classification. Yeah, if our data is in continuous, it's better to transform into some discrete data or binary data into. Or if the data already categorical, but the range is very big, it's very large. The categorical attribute has large number of value. For example, it's very large. So we want to make this into smaller one. For example, the original one from 1 to 100. So we transform into from 1 to 5, for example. Okay. Okay. This one, binarization. Binarization for some classification algorithms, usually it requires data to be in form of categorical attribute. Okay. Or maybe, for example, we have this categorical value, already in categorical value, but then the algorithms, it needs us to be in binary. Yeah, some algorithms like this. So what we can do, for example, we can transform into like this. So here the categorical value, for example, this is Likert scale, and then this is the integer value. But then the algorithm works better if they process binary value. So instead of using 0, 1, 2, 3, 4, we use three new features, x1, x2, x3, which is the breakdown of this x value. Yeah, for example, 0 represented by 0, 0, 0. 1 represented by 0, 0, 1. And 2 and 3 and 4. Yeah, like this. Or if we have, we also can use more value if we think like this. Why is not, let's say, why it is not, it looks like doesn't have a pattern. So instead of using 3 new features, we use 5 features. So 0 means 1 in the x1 and the rest is 0. 1 is x2, 2 is x2, 3 like this. Yeah, these are two example of converting from categorical into binary. Okay. Discretization for continuous attribute. Okay. The easiest one, we can sort the attribute value and then divide it into n intervals, as, and then we map all the value. For example, we have, this is our data. Yeah, 5, 10, 12, 13, 15. For example, we have maybe 2 and also 3. Then we sort this one. Okay, so this one, the smallest one will be 2, the highest one will be 5. Okay, then we divided this into 3, for example. So the range is 13. Okay, range is 13. So if we divide it into 3, maybe the 13 divided by 3 is around 4. So maybe 2 to 6 equal to 1. 7 to 11 equal to 2. And then 12 to 15 equal to 3. Okay, so this 5 becomes 1, 10 becomes 2, 12, 3, and continue. Okay, this is the easiest one. Okay. Discretization also we can use unsupervised or supervised methods. Okay. Oh, this one, simple discretization. If we use equal width, so like for example like this, we try to make it the range are the same. Okay. This is the most straightforward way. Okay. But in this case, this is the most easiest one. But then, if we have outliers, the outliers may not be C in the result. Yeah, because we use like this. Okay, screw data is not handled well. Okay, equal dips partition, here it divided into n intervals, and then it's containing approximately the same number of samples. Okay, so for the first one, this is the range. Okay, and then we divide it into the same interval, and then all data, let's see in which interval. Okay, But for equal dip, it means that we divided in each range, number of samples should be the same. So this the first one we divided the range based on the value here, but for the second one we divided based on the number of the sample. Okay, so if the data, for example, most of the data is here, maybe this one only like this. So I think maybe for this one, the cutting point will be like this. Yeah, because we want to make sure that for each range, number of samples the same. Yeah. Okay. Okay. So this one, the second way, it's usually good for if the data is skew data. Yeah. For this one, it's not skew data. And next, this one is discretization without using class label. Okay. Unsupervised discretization. So here, although the data is supervised, but in discretization process, we ignore first the class. Yeah, so the class information is not used. Okay. Discretization of continuous attributes involve how many categories on how to map. Okay, this is for example, this is the data. Okay, uh, this one, if we want to divide it in based on the equal interval width, and this is the equal frequency. Yeah, if we divide it, this is the first, that one equal width, this is the equal frequency, equal dip. But this the fourth one, if we divide it using k-means algorithm. Yeah, but this one will be learned when we learn about clustering. Okay, so we also can use k-means to discretize our data. Okay. Categorical attributes with too many value, it is better if we also categorize that into the small number of attributes. No, smaller range of the attributes. Okay. Next is data transformation. So data transformation, we transform the data into other value. Smoothing is one example of data transformation. Aggregation that we just talked before is also example of data transformation. Generalization of the data of also the data transformation. And the new one is this one, data normalization. So what is data normalization? Sometimes, for example, our data, let's say we have attribute age, we have attribute salary, for example. And then from the age and salary, let's say we have the another attribute, maybe this one is health, happy or not, for example. Okay, for example. Uh, then if we want to use this one, x1 and x2, to predict y, the class, we see that the range of the age may be 15, the oldest one may be 75. Can be someone age more than 100? Yeah, maybe, but only few. Yeah, okay. Okay, let's say the highest one is 100, for example. But the salary maybe from 1,000 until maybe 100,000, for example. Yeah. So let we see that the value of attributes x1 relatively smaller than value in attribute 2. Okay. So when we calculate one data, for example, this is one data, this is the second one instance and the second instance. if we calculate the similarity, for example, of these two data, then because the salary x2, the value in numbers is higher than age, then maybe salary give more influence to the result. In mathematics, for example, if you add linear distance, for example, x1, x2 square, y1, y2. Sorry, this is x, y, z, y2 square. Okay, then we see y value is higher than x. So in terms of calculation, mathematically, salary will give more influence than the age, which is not really true, maybe. Yeah, because this is not correlation. But in mathematically, salary will give more influence because the number is higher than x. Okay, so how to deal with this case? We can do normalization. So with normalization, all of these attributes will have the same range. Let's say all of them will be transformed into 0, 1. Salary also from 0 to 1. So here, because in terms of the number, between 0 and 1, 0 and 1, they are in equal value. Okay, so there is no attributes will be more influenced than other attributes. Okay, yeah, because the number value already equal. So this is the objective of normalization. Yeah, we try to change or transform our data into specific range. For example, to make it fair between attributes. Okay, normalization, data normalization, there are many types of data normalization. For example, min-max normalization, z-score, or normalization by the decimal scaling. Okay.
Uh,
Okay.
Dr. Farah, can I
Yeah.
ask?
Yeah, sure, you
Um,
can ask.
what if the data for the age was set in range and then they would fall in that specific range, and then you have like five range of ages, for example 15 to 20, and then 21 to 26, and so on and so forth?
Oh, okay. Let me give you example. Okay. So here, this one is the normalization, min-max normalization, for example. Okay. So if the original data, for example, the youngest one is 15 and then the oldest one is 60, for example, yeah, from our data. And then this is data 1, data 2, data 3, for example, 20. Okay, this one. First, from this data, we try to find what is the minimum value and what is the maximum value. So here the minimum is 15, maximum is 60. Okay, then the easiest one, we can transform that the x value equal to the original x minus the minimum divided by maximum minus minimum. Okay, this is the very simple one, different with this. Okay, this is the simplest one, for example. Okay, so here 15, the normalized value, this one equal to 15 minus 15, the minimum one, divided by 60 minus 15. So it will be 0. 20. 20 minus 15 divided by 60 minus 15. So it will be 5/45. sorry, will 09. Eh, 4. Sorry. Okay.
Uh,
Then this one,
okay.
09. Yeah. This
Okay.
one,
Dr. Vera,
60.
I asked if this is okay. This is for one variable, but what about like the one variable and another variable is actually not the range not the same. What about that?
Yeah.
Can we also treat also like this one for all the variables?
Yes. So
But
this
okay.
mechanism,
Uh-huh.
we do this for each attribute.
Yeah, for each attribute. Oh, okay, okay, okay. Yeah,
Yeah.
okay.
So this one for the age, we do that x equal to x minus min max minus min. But this one for age. Then for salary, we also use this value. But then maybe the minimum value is 1,000 and maximum value is 100,000.
Okay, got it. Yeah, I got it.
Okay. Okay. Any other question? No. Okay. So here there are many example or formula that have been proposed for data normalization. Yeah, we have min max normalization, z-score normalization. We also have standardization, for example, here. For normalization in Python, this one, you can explore from package sklearn.preprocessing. Yeah, this package will provide us many data preprocessing techniques, especially for transformation. Okay, it will give so many different type of data normalization. Oh, this one I just okay. Uh, Beside this normalization, we also have like attribute or features construction. Yeah, the one that in previous slides. Okay, so this one means that new attributes construct from the given ones. Okay, so we also can use other transformation, for example, using logarithm for this one. Oh, and any other distribution, for example, square roots, uh, other things, and also we have standardization. Yeah, so for if the normalization, we normalize the data into the range 0 to 1. For standardization, maybe we have to normalize into the standard based on standard mean and standard deviation of the value. So here the min max value, that one I mentioned before, we don't care about the data, the mean and the standard deviation of the data. Yeah, we just care about minimum and maximum. But standard deviation, but the data standardization, we transform into the new range, the data, but then the new range will be depend on the mean and standard deviation of the data. That's called standardization. Yeah. The package here also provide us with the standardization of the data. Okay, any questions? Practical question also okay. If you want to ask about, for example, the well, if you want to try using the Python, it's also okay. Okay, already finished for data preprocessing. Okay, any question? Or if you want to ask a question for the final project, is also okay. Okay, please, if you have any question.
No, for me it's clear.
No, for now. This one, can
Doc,
you see? Yeah,
I have question, Dr. Farah.
yeah.
What if you have the class as 0 and 1 to represent yes and no, but the
Mm-hmm.
other attributes are listed as 1 to 5? Is that still fine, or should I transpose also the attributes with 1 to 5 scale?
Okay, it will be different. It will be depend on the algorithm. So, for example, later if we uh, want to use decision tree, for example, yeah, you can you we can convert into 0 and 1, or we can still use 1 to 5. But then the data, sorry, 1 to 5 is continuous data or categorical data.
Categorical data.
For categorical data, I think it better to use on as it is. Using categorical is okay, 0 to 1. We basically the important one, if we want to normalize, for example, if we have more than one attributes, but then the range are very significantly different to each other. For example, this one, income, the range is 3,000 into 100,000. The age, the range is 1,000 into, 10 to 80. And the gender, this is maybe 0 or 1. Yeah. So if you see that this, because these three attributes, the range are very different to each other. So it's better for us to normalize this. Okay. But in your data, for example, you have x1, x2, x3, and also you have class y 0 1 0 1, for example, and x1 x2, the scale is only 1 to 5 1 to 5 1 to 5. So this is okay, no need normalization. Why? Because the range of x1 and x2 and x3, they are all in the same range. Okay, so no need to do normalization unless you prefer to use any specific algorithm that require us to change into 0 and 1, into binary, for example.
Oh, thank you, thank you.
Okay, yeah.
Okay,
So the
so
key point is the range between attributes. Okay.
okay, so okay, the range. Okay, okay,
Mm-mm.
but okay. What again? What is for this one? This is we going to classify, right? No, cluster classify. No, we are
Uh,
going to
do
depends.
for
Yeah.
every,
Mhm.
yeah, for depends on the algorithm. But for example, clustering also can clustering for some data also need normalization.
Yeah.
Prediction also need normalization.
But can we? I would say like from I would say that from the historical data, can we? I mean, we calculate, but after that we
Mhm.
predict what we'll calculate like that. I
Yeah, yeah,
mean,
yeah.
yeah. Is it? I mean, I'm asking that one actually. That we calculate something first, and then we got the value right, and then we predict that value based. How to do it? I mean, this is
Uh, let me try to understand your question. For
okay. Okay.
example, we have
No, no, no.
10 data, historical data. For example, 1 to 10. And then we normalize this value.
Yeah, okay. And then from
So
one to
this,
ten, we actually can have we can calculate something out of that one or 1 to 10.
yeah.
Let's say yeah.
Okay, then we predict y, for example.
Yeah,
Okay.
y. We got the value of the y. Okay. And then can we do another data mining based on this one? I mean, from y we classify into binary or like we make it into three different cluster and then we do the classification on that one.
Yes, yes, yes. We can do that.
Oh, okay. Then that is okay.
So using the new value,
Yeah, with the new
then
value.
using new value to do the algorithm.
Okay.
right?
Yeah. Yes.
Yeah.
Yes. Okay.
Yeah.
And the final one.
That. Hmm.
It's this one is very close to the. I would say that the logistic regression is 0, 1. I would say if the case is 0 and 1. So
Mhm.
in the logistic regret is logistic regression is included in data mining the classification or like
Oh, regression. They
logistic
sorry,
regression zero
regression.
one yeah.
Logistic. Yeah, logistic regression basically is the statistic tools, right? Approach.
Yeah, that I
Yeah.
know, but this one
And
it's looks so similar. Yeah.
yeah, because the basic knowledge of data mining is statistic. So they both have the same parents, I can say.
Oh, okay. So
Yeah.
I think should be the same. Yeah, okay. Just like cluster, like
Mhm.
yeah, okay.
Yeah. So if we want to learn data mining, we should have basic statistic. Same like regression, right? We should have basic statistic skills.
Yes.
Mhm. I think start from these recent years. In my point of view, uh, all departments should learn about data mining, just like statistic. Social learn statistic, engineering learn statistic, science learn statistic, and also this data mining becomes just tools, right? Dr. Yogi in ergonomy also use data mining, right?
Yes.
Mm-mm.
Just recently, I mean, people in ergo people abuse the data mining in the ergo. Yeah, just recently this year, but it's so hot, so I have to catch up with the researchers worldwide because they already at that stage. I'll be like, oh, okay,
It's okay. You can catch up.
yeah, with your help.
No worries. Yeah, so statistic, regression, data mining, they are from the same root, I can say. Statistic is the root. Okay. Dr. Yogi, the problem is not after we normalize the
Mm-hmm.
data and then we can
Mm-hmm.
apply algorithms. Of course,
Mm-hmm.
this is the point of normalization. But how
Mm-hmm.
if the new data is coming here, the 11th data, for example. In historical, we have only 1 to 10.
Mm-hmm.
Okay, so this equation x minus mean, max minus mean, it means that the minimum value is minimum value from 1 to 10. Maximum value is maximum value from 1 to 10. Okay, but how about the new data, the 11 data number 11, this one not included into this equation, right? So uh, beside normalization, we also have denormalize. How to write? Denormalization. It means that after we normalize the data to build the model, let's say if you are familiar with regression, then I can use analogy like from 1 to 10 we normalize, and then from the normalized data we build the model, just like in regression. Yeah, you can imagine this is the regression model using normalized data. Okay, but then if we want to calculate, for example, the accuracy, or we have the new data come here. So it means that the data should be denormalized. If you ask me, oh, okay, so
Mm-hmm.
how big is the income if I want to get a class y equal to what, for example? Yeah. So if you read in the package, sometimes in the math, don't worry, the normalization also have the package in the Python. So we can just call
Okay.
easier like this.
Okay. Can I show you my something? I want to share the screen
Yes,
a
yes.
little bit.
Okay.
Okay.
Wait,
Yeah.
I can
Yeah.
share.
Okay, so my turn. Okay, so here actually, sister, I have 55,000 data. This is the household data from the questionnaire collected from the Philippines. One island is actually in the Philippines, one small island.
Okay.
In here, okay,
Okay.
I have the data of the, for example, this is the data of the roof building materials. This is the wall building
Mm-hmm.
materials. Disaster
Categorical, right?
experience. Yeah. So
Okay.
everything in here is actually the categorical. Okay. This is
Yeah,
a very
yeah.
category. Okay. Oh, no, this two is categorical, but this one is the scale.
Binary.
This is the experience can be 10, 30, and so on.
Oh, okay,
And
okay, okay.
yeah, so E3 to E7 is not equal. I mean, this is the how is it that the experience. These two is actually the how is it that the categorical. Okay,
Categorical.
and then this one is the number of elderly, number of people with disability. This is number of children and
Mm-hmm.
pregnant, and then this is the income of
Mm.
the house. So this is actually that one. And then I have another data is actually that uh, this one is actually a percentage. No, some is actually percentage. For example, this is the percentage. This is the
Mm-hmm.
education. This is the education. This is the appliances, the monetary appliances. This is
Yeah.
vehicles, and then uh, this is the I forget. Oh, this is number of emergency. I mean the some actually not equal, some percentage,
Yeah,
some
yeah.
this one, and
Okay.
so on. Okay, if this one, if I do not want, if I would like to do unsupervised, because I don't know,
Mm-hmm.
we can calculate, how this is actually calculating the vulnerability of of a place. They have they establish, some researchers actually establish the equation how to the the equation of vulnerability. But I would like to do something like clustering only of
Yeah.
these 50 something thousand. I would like to see the pattern, or like the cluster, instead of
Yeah.
you know usually people will just calculate this one first, and then they will cluster that one, whether there's high vulnerable,
Mm-hmm.
low vulnerable, and so on. But that one, by the calculating, like they calculate something, and then
Mm-hmm.
they cluster. But can I just cluster
Mm-hmm.
this one directly? I think I can do it like
Yes.
something. Yeah, yeah.
Yeah. You
So
can do.
mhm.
But you it's better if you normalize the data first, because that one, the range for income is much
Yeah,
more
this one,
higher
yeah, yeah,
than.
yeah. This is
Yeah.
this is so high, the variability. I mean, yeah,
Mm-hmm.
this
Mm-hmm.
one. Okay, so after normalizing everything, then
Mm-hmm.
yeah, we can do the, yeah. Well, I don't know.
Clustering.
I have to
Yeah.
follow your
The
class.
clustering.
Yeah, we do clustering, because people usually they calculate this one first, then they do the clustering. But I don't want to calculate that. Can I just have the log? The based on this one, I can just cluster it immediately. We can
Yeah.
do it, right?
Yeah.
Yeah. See how
Yeah.
many I have?
Definitely, you can do
Five.
that. Don't worry.
Okay, so I got it. Yeah,
Mm.
at least I can work something with you
So
on that one.
yeah.
I
No
published
worry.
yeah, I published that one already, but I would like to do another publication out of that one with another method.
Using different methods, right? You mean?
Yeah, using different method. Yeah, using very different
Okay.
method. Yeah.
Mhm. I think you also can do the program because
Oh,
it's very easy.
really? Oh, okay.
Really?
Okay. Yes, for you easy. For me, like, oh.
No, no. You just see, like, in the my slide previously, when I give some picture of my code, the one, it
Mm-hmm,
is
mm-hmm.
really as it is. I mean,
Oh,
in
really?
my
Oh,
program,
okay.
yes,
It looks
only
easy then.
very. Yes.
It looks easy then. Okay.
So everyone can use that. Don't worry. Michael also can teach you.
Oh yes, he's expert.
Yeah. Okay.
Oh,
Any question? Hi, Michael.
You're there.
no, no question from me.
You want to do what? Clustering? How say that? Investment or something? You do that? I mean, like,
I think for Michael, for
yeah. What
investment,
did you?
it's more like
Yeah.
prediction, right, Michael?
I want to apply it in forecasting.
Mm-hmm.
Yeah, then
Oh,
Then you can use, I think, next week we start with classification, decision tree, and then after that, the next 2 weeks will be neural network. Neural network is the uh, basic theory for deep learning right now, very famous, right?
yeah, yeah, I'm interested.
Mm-hmm.
yeah, me too. I'm going to. I want to publish that one with another data mining technique.
Oh,
Okay.
okay. Okay, so until this part, so these 2 weeks, I can say that although it looks like simple, we tell about data collection, about data preprocessing looks easy in terms of theoretically, but when we really collect the data, yeah, it's very difficult. Okay, so that's why data is expensive right now.
Very expensive. Yes,
Mm-hmm.
that one.
Mm-hmm.
Yeah.
Okay. Okay, any question from the students?
No, sir.
Yeah.
I think it's
Okay.
better for them to start getting the data. I think, yeah, right,
Yeah, 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 exactly.
Dr. Farah. Yeah,
Right,
because
right.
if they have the data from the government or like the anything like like what I did before. I mean, what I show. I think it will be great for their for this class if they can get the
Yeah,
data as soon as possible. Yeah.
yeah, sure, sure. So maybe after the class, for example, next week I teach about that data classification. If you already have the data, then you can try directly, and if you have any question, you can ask directly to me. Or maybe you can also use some benchmark data from UCI, for example, for just for practicing. Okay. Uh, no question. If no question, I think we can finish. Can we finish our class today, Dr. Yogi?
Oh yes, but I would like to consult with you after this one, and I think
Okay,
Admin
okay.
Ong wants to, because we have the data already. So I would like to do it as soon as possible. So
Yeah, yeah,
yeah,
sure.
okay.
Okay. Okay. So if no more question, I think we can finish for today's class.